students, in the last class we have seen Hahn-Banach theorem on vector space, that is a generalized vector space. Now we are having Hahn-Banach theorem on normed spaces. Now here we are having X as a vector space. Suppose P is the subadditive, or we can say that P is the functional defined on a vector space X. Then P is subfunctional if there exists a subset of X which is having F as a functional, then we can say that F bar is the extension of F on X. F is the functional on Z means F bar is the functional on X. This F bar is called as the extension. Now the next theorem is Hahn-Banach theorem only on normed spaces. In the statement it is given that F be a bounded linear functional defined on a subspace Z of a normed linear space X. So here it is given that X is a normed space and F is the bounded linear functional defined on the subspace of X, and there exists a bounded linear functional, say F bar on X, which is an extension of F from Z to X. Means here we have to prove that if F is a bounded linear functional defined on a subspace Z of a normed space, then F bar will be the extension of this linear functional on X, we have to prove. Now here this extension of F from Z to X we are having, which has the same norm as F. So F is defined on a normed space capital X, therefore it is having a norm as same X. So F, this extension as well as the bounded linear functional F has the same norm. We have to say that norm F bar X equal to norm F over the subspace Z. And here it is defined that norm is always defined as supremum of mod F of X. The same will be applied to extension also. This we have to prove. Now to prove this, we will first take that X is a normed space, Z is the subspace of X. If suppose Z equal to having only one element, say 0, then it is obvious that its extension will be having 0 only. Means if we assume that the 0 function as extension, then we can say that there exists an extension and theorem will be proved. Now we assume that Z is not containing only 0, it is containing the elements. In that case, see mod of F of X, generally the definition of the boundedness, we can write mod of F of X is less than or equal to norm F norm X. And here F is defined on the subspace Z, that's why here we write Z for all X belongs to Z. Here, to prove that there exists a extension, we can make use of the previous theorem, generalized Hahn-Banach theorem. For that, we can define a subfunctional. See, if we are having a subfunctional and if we take P of X is less than or equal to F of X, then we can show that there exists a linear extension. So for that we define one real functional P on X. So how we define is P of X will be norm F into norm X, where norm is defined on the subspace Z. Here P is defined on X, therefore every X belongs to X. So we prove that this P of X is subfunctional. Subfunctional means we have to prove two properties. One is subadditive, another one is positive homogeneous. Now to prove it as subadditive, we can take P of X plus Y equal to, by the definition which we have assumed, we can write norm F into, in the place of X we are having X plus Y, so we will write X plus Y. So the property of norm is that norm of X plus Y is less than or equal to norm X plus norm Y. Therefore, it will become less than or equal to P of X plus P of Y. for all x comma y belongs to x. This proves that P is subadditive. Now we have to prove that P is positive homogeneous. For this we can take P of alpha x equal to, where x is there we substitute alpha x. By this we get that mod alpha into P of x because of the property of a norm. So this implies that P of x plus y is less than or equal to P of x plus P of y. From this we can say that P is subfunctional. Now P is subfunctional. Then next thing we have to prove is mod f of x is from 1 and 2. See, this is equation 1, mod f of x. Equation 1 is we are having extension of norm and f, as well as here mod of f of x less than or equal to norm f into norm x. See, from these two we can observe that norm f of x is, this value is replaced by P of x. So here, to use generalized Hahn-Banach theorem, what we need is, we need a subfunctional, we need a linear functional, we need one property that mod f of x is less than or equal to P of x. All the three properties are there. Hence, by generalized Hahn-Banach theorem, we can say that there exists a linear extension f bar, on which it is a linear extension on f and which satisfies the same property, mod of f bar of x is less than or equal to P of x, but P of x is this much. Now, if we take supremum on both sides, we get supremum of mod of f bar of x equal to supremum of this, when norm x equal to 1 means, here if we substitute this as 1, we can observe that if we remove supreme, this will become norm f bar x. This is from equation 1. Here it will be replaced less than or equal to, it is 1, so it is norm f. And norm f over defined over x is less than or equal to norm f defined over z. Similarly, we can prove that norm f bar defined over x is greater than or equal to norm f over z. So it is proved in this manner. We know that z is subset of x, therefore this x belongs to z, norm x equal to 1 is also subset of the set with norm x equal to 1. So hence this supremum of this value will be greater than the supremum of this. And here, as here we are taking x, here we are taking z, z will be limited, that's why x value, the value which we are taking in x will be greater than or equal to. This can be written in this manner by previous one. So hence we get that norm f bar will be greater than or equal to norm f over z. So from equation 4 and 5 we can say that both are equal, which implies that there exists a linear functional. There is a linear functional means there exists a linear extension of that functional f. So this is the Hahn-Banach theorem on norm spaces. Now we will see the next one.